In this section, we're going to talk about continuity of a function. So we have three conditions for a function to be continuous. The first is that the function has to be defined at that specific value, which means our x value is in the domain. The second is that the limit as x approaches that value has to exist. And the third, this is the key one, this one a lot of us miss, is that the limit as x approaches that value of f of x is equal to the function value. So they have to match. All right, so let's practice. So g of x is equal to x squared minus 4x minus 12 all over x minus 6. And we want to know if this is continuous at x equals 6. So the first thing says it has to be defined, meaning x equals 6, here's my value, this has to be in my domain. Well, if I plug 6 into my denominator, I get a 0. That would be undefined, so therefore this is not continuous. There is a hole there. It doesn't work. So we can't do it. I mean, yeah, we could take g of x, and we could say this is equal to x minus 6 times x plus 2 over x minus 6, and we could simplify this, but if I actually graph the original function, this doesn't work. So this is what we call a removable discontinuity. There'd be a hole when I made that graph, but this is not a continuous function because x equals 6 is not in the domain of that non-simplified function. All right, let's try another one using a piecewise. Is f of x continuous at x equals negative 1? Well, in order for it to be continuous at x equals negative 1, it has to be defined. So when x is equal to negative 1, from the left, 3 times negative 1 minus 1 is equal to negative 3 minus 1, which equals negative 4. So by this definition, f of negative 1 does equal negative 4, but in order for it to be continuous, that's going to have to hold as the graph continues right here and goes to the other side. So I'm going to look at 1 squared plus 5 times 1, negative 1, times 5 times negative 1. So here I have 1 minus 5, which equals negative 4. So this tells me that this is continuous. The value of the function is equal to negative 4. This is showing me that the limits from the left and the right are the same and that it worked. All right, let's try the other side. F of x continuous at x equals 1. All right, well, f of 1 by this definition would be 3 times 1 to the third, which would equal 3. And then we need to know as we come at it from the left and the right, is it the same? So as I'm coming at it from the right, we know it's equal to 3. As I'm coming at it, approaching 1 from the left, I'm taking the limit as x approaches 1 from the left of x squared plus 5x, because that's where the graph is there. So this would be 1 plus 5, which is equal to 6. So because these limits don't match, this is not continuous right there. There would be a jump. So if we were to graph this, we would see we couldn't draw it without lifting our pencil up off the paper. All right, so that's another way to judge. When you're drawing a graph, if you have to stop and lift your pencil up to go to a new spot, the line isn't continuous, it's not a continuous function. All right, so a few common ones that we use a lot. A polynomial function is always continuous everywhere. Rational functions are continuous except for where the denominator equals 0. Sine and cosine are continuous everywhere, and tangent is continuous as long as cosine doesn't equal 0, as long as the denominator doesn't equal 0. If we're dealing with a composition of functions, f of g of x, it will be continuous at x equals a, provided g of x is continuous at x equals a, and f of x is continuous for the x value that's equal to g of a. So they have to both be continuous. For a radical function, the nth root of x is continuous as long as n is even and the radicand, the number underneath, is greater than 0. It's also continuous provided n is odd and x is a real number. All right, let's throw in a bit of review. Evaluate the limit as x approaches infinity of 2x plus 1 over x to the third. So this is kind of using a lot of techniques we've learned throughout chapter 2. So the first thing I know with my limit laws is I can actually take the limit as x approaches infinity of 2x plus 1 divided by x, and whatever that is, I'm allowed to cube. Okay? I also know that if I'm looking at something that I'm taking the limit, and the degree of the numerator matches the degree of the denominator, the limit is just equal to the ratio of those coefficients. So in this case, x to the first and x to the first, this is the same. So my ratio, 2x to x, is 2, so this limit is just equal to 2, which I'm cubing, and I get 8. Okay, so we want to put together everything we know about limits with this now continuous idea. So this brings us to what we call the intermediate value theorem. And it says if f is a continuous function on some interval from a to b, and L is any number between f of a and f of b, then there has to be at least one number, we're going to call it c, between a and b that gives me that value of L. A picture helps. Alright, so here I have some random continuous function. I'm drawing it without lifting my pen up. And it's continuous on this interval. Here's a, here's b. Okay? And then I have some value, L, that's going to be between a and b. In this case, I have it labeled as w. That was my picture. So we're going to label this L. So here's my L. And it's somewhere between f of a value and f of b value. So because this is a continuous function, it means that this has to drop down. There has to be some c in between a and b. That's what the intermediate value is telling me. It's saying there has to be another input that gives me an output between those other two outputs. All right, so let's verify that. So I have f of x equals x squared plus x minus 1 on the interval from 0 to 5. We want to verify that the intermediate value theorem applies to f of c equals 11, saying that there is some c in between that's going to equal 11, and then we want to find out what that c is. So the first thing I have to do is find out what is f of 0. So f of 0 is 0 squared plus 0 minus 1, which equals negative 1. F of 5 is equal to 5 squared plus 5 minus 1. So that would be 25 plus 5 is 30. 30 minus 1 is 29. And we can see here very clearly that f of 0 is less than 11, which is less than f of 5. So that part holds. So we know that there has to be a c that exists to make this true. So that means I want to know, when does my function 11 equal c squared plus c minus 1? And we're going to solve for c. So 0 equals c squared plus c minus 12. I can solve this by factoring. This is c plus 4 and c minus 3. And I get two values of c that will give me that output. I have c equals negative 4 and c equals 3. These are not both the answers because remember it has to be on this interval 0 to 5. So the value that makes this work on the intermediate value theorem is c equals 3. And anytime you're asked to do an intermediate value theorem problem like this, you would need to show me, right? You need to show me very clearly that this is true, and then you can show me the work to solve for c.